Okay guys, 5 past, we'll get started. Okay, so on Thursday's lecture we had a little bit of a look at recrystallization. Okay, now recrystallization is in a bit very important to industrial, commercial processes and things like that in material science, and it also is dependent on aspects of nucleation, growth, diffusion and kinetics. Okay. So we learnt that the process is thermally activated. Okay, there's a critical temperature for recrystallization to occur. Okay, there's also a critical amount of deformation required for recrystallization because nucleation of new grains is essentially driven by the amount of pre-deformation in the material. We also had a look at two different types of recrystallization that can occur during processing. So static recrystallization, where we impart some form of deformation, some degree of deformation on our material, and then take our material and then go and anneal it at a certain temperature for a certain amount of time to invoke static recrystallization, which is a very controllable process, but also dynamic recrystallization if we are actually deforming the material at a temperature above the recrystallization temperature. So we seem to have a cyclic loop of deformation and recrystallization occurring at the same time during processing. We had a little bit of a look at how recrystallization can affect the texture of materials and the properties of materials. Okay, so that we had a look at the example of hot rolling at 320 degrees centigrade versus 350 degrees centigrade for the magnesium ZKC alloys that we did for Volkswagen some time ago. And we can see here, by destroying some of the rolling texture using recrystallization, and we were able to get extensive elongations out of the material as opposed to imparting strong texture on the material. Okay. We then had a little bit of a look at the actual mechanism for the formation of new grains and how the nucleation of new grains is actually driven by deformation and by essentially the entanglement and localization and formation of dislocation cells in our material. Okay, so our dislocations that are a result of deformation start to form cells within the material. Okay, and within those cells, our dislocations are essentially annihilated, and these dislocations will become new grain boundaries under the correct conditions. Okay, some examples of dislocation cells in material after deformation. Had a little bit of a look at the kinetics of recrystallization. Okay, how our nucleation time is equivalent to the amount of deformation we put into the material. Once nucleation and growth occurs, it's essentially a linear increase until we get to a point where the new recrystallized grains start to impinge on one another and can't grow as quickly anymore because they're essentially pinned by the other growing grains around them. Okay. Some of the, we had a little bit of a look at impurities. Okay, how impurity atoms or impurity particles, and depending on their dispersion, might affect recrystallization rates in our material. Okay, and depending on the size of them and the spacing on them, we can either enhance recrystallization or slow down recrystallization processes depending on what we want to do. We had a little bit of a sidestep look at superplasticity, how we want to avoid recrystallization in these particular materials by strategically placing very, very fine particles along grain boundaries. Okay. Right. But for today's lecture, we're going to be focusing on grain boundary and surface diffusion. Okay. So our materials, they're not completely homogeneous materials. Okay. Most materials you're going to come across in nature are going to be polycrystalline. Okay. And they're going to have some surface about them that's exposed to either the environment or another type of atmosphere or material. Okay. And what we find is that grain boundaries and surfaces diffuse or allow diffusion of different species across them and into them, through them, at different rates depending on a number of different variables. And these are things that we have to take into account when we are utilising diffusion and diffusion kinetics in altering our material or how they might respond to a given environment. Okay, so grain boundary diffusion we'll look at first. So grain boundaries, okay, and throughout the text here I'm just using GB, just as a simple symbol. Okay. Diffusion plays an important role in many processes in engineering materials. Okay, so grain boundaries are involved in things like creep, the ability to sinter something, diffusion-induced grain boundary migration. Okay, so impurities moving in and out. It's closed down, isn't it? Has it been up there at all? When did it stop? All right. Okay, so grain boundaries, important. Okay, so grain boundaries actually define many different types of processes when we're talking about our materials, how we can deform them, okay, and their performance during service depending on what's around them. Okay, so grain boundaries are particularly important when it comes to something like creep. Superplastic forming is actually a form of creep, for example, or room temperature creep in our materials. Diffusion-based or diffusion-induced grain boundary migration. Right, so impurities, basically grain boundaries are impurity superhighways. Okay, if we want to diffuse an impurity in or out of our material, it's usually done via grain boundaries. Right. We'll get onto a few examples as we go through the rest of the class. Discontinuous reactions, okay, such as precipitation or coarsening, okay, recrystallization and grain growth. All very important aspects where the grain boundary and the characteristics of the grain boundary come into play. In a similar way that it's very, very difficult to do calculations for things like nucleation, growth, crystallization, things like that. And we use kind of roundabouts ways of defining this, just like our classic nucleation theory. Advances have been made in understanding grain boundary structure. Okay, so we now have characterization techniques where we can actually observe the grain boundaries quite well. Right, so advent of TEM, probably about 30 years ago, 40 years ago max, we can actually observe the structure of our grain boundaries, okay, as opposed to surrounding crystal structures in high resolution TEM, and atom probe tomography, where we're pulling the material apart atom by atom, then doing a reconstruction of that. You can actually see where all atoms are sitting on grain boundaries. You can do concentration profiles within these systems and look at segregation profiles and things at grain boundaries. Where are things sitting? What is their concentration? And what were the experimental conditions that led to that? Okay. So the associated mathematics and crystallographic relationships are very comprehensive, and they're going to be dependent on the system. Right? and even more so dependent on what's actually happened to that material. And a lot of the time this isn't translatable from system to system. The method is, the mechanism is, but the actual numbers that we would use on a calculation are not. All right? So again, this type of science is something that's measured and observed. But what we're going to do today is just give a basic view of the concepts of grain boundary diffusion, some of the equations that are used in a very, very generalised way, similar to other diffusion-based processes. We actually touch on Fick's second law again today. All right. The first thing we're going to look at is the actual diffusion into a grain boundary. Okay? Now it is a very complex kind of setup. All right? So this is a very, very simplified version, but hopefully it's going to give you a bit of an idea about what's going to be happening here and how we would approach that in terms of diffusion kinetics. All right. So most mathematical treatments of grain boundary diffusion based on the Fisher model. That's what we're focusing on today. Okay. All this does is describe diffusion along a single grain boundary in the most simplest case that we can really think of. All right. A grain boundary perpendicular to the surface of our material. So if that's the surface of our material here, out here is whatever atmosphere or next phase is present. Okay, whether it's a continuous phase or a discontinuous phase. Okay, here's our solid material. Here we have essentially, probably, we're going to say a grain of material, our matrix or our lattice on either side, and here's our grain boundary here. Okay, so the way the Fisher model works, the grain boundary is represented as a high diffusivity, uniform, isotropic slab embedded in a low diffusivity, isotropic crystal perpendicular to its surface. Okay, so a lot of assumptions there. Okay, this thing in here, isotropic slab of material where the diffusion coefficient, dB, or diffusion coefficient of the grain boundary, typically is going to be much, much higher than the diffusion coefficient of the lattice, okay, within the body of the grains and the materials themselves. We describe the grain boundary, okay, by two physical parameters, the grain boundary width, okay, delta, and the grain boundary diffusion coefficient. And we've also got the basic assumption, which is true in I think 100% of cases, that the diffusion coefficient of the grain boundary is much, much greater than that of the surrounding matrix. Okay. So we kind of get that. That's what we're trying to describe our grain boundaries with, and see if we can define how fast these things are going to diffuse, or diffuse elements. And for this case, even though we're kind of concentrating on bringing things in from the atmosphere or from the surface of the material, it also works in the reverse direction in getting material out of the bulk and through to the surface. Okay, both things happen in nature, just depends what the forward reaction is. Can anyone think of any examples where we might be trying to bring something in from our atmosphere into our material? Trying to dope our system with something from the surface? Yeah, so carburization is the first one. We've got a gaseous atmosphere that's rich in carbon or carbonated compounds. We're trying to bring carbon into the surface of our material. Can anyone think of a situation where we might be going in the opposite direction? Probably a bit harder to think of these ones. So situations where things might come out of our grains and through to the surface are de-alloying events. All right? So sometimes the environment or even an electrochemical driving force might make certain elements want to leave the material. Okay, it can happen in nature or under artificial driving, so electrochemistry and things like that. We can force elements out of the material, moving them from the surface, from the grain boundaries. One naturally occurring thing happens like this is in brasses and brass fittings. If you've got a very high zinc content in your brass fittings, which most of them do, 30, 40%, anything over about 15% zinc, okay, zinc will de-alloy, a process called dezinkification. And what happens is zinc atoms want to interact and react. They're very, very mobile. Okay, they'll find themselves a grain boundary and start to migrate to the surface and then oxidize, okay, or dissolve in the surrounding environment. Okay, so that's an example of ions wanting to disappear out of here. Also remember that the grain boundary is an area of higher structural energy, okay, and it doesn't necessarily have a nice fixed regular lattice pattern. So often impurities in our material are attracted to a grain boundary to minimise structural energy. So if we've got a very, very small atom that doesn't like being in the lattice because it doesn't fit in the lattice very, very well, it's going to migrate to the grain boundary because there's more gaps and spaces for it to actually sit in. Okay? So what we find is a lot of our impurities will end up at grain boundaries because of this reason. And then, once they're in the grain boundary, they're free to move up and down and round and round our material in the grain boundaries more freely. Okay. All right. So, in a typical diffusion type experiment, okay, for a grain boundary setup, a layer of foreign atoms or tracer atoms of the same material is created at the surface of the specimen, right? And then it's annealed at a constant temperature for a given amount of time. So this is how we run a typical experiment. Right? We know a lot about our material already. We're going to go and heat it at a certain temperature for a certain amount of time. This starts to generate our data points to determine diffusion rates of elements in our material. Okay? The surface condition, okay, what we can do to supply this layer of atoms or something on the surface, there's a couple of different ways. Right? So we can be in contact with an environment, just like in the carburization process, that has an infinite number of carbonated molecules. Okay? So that's kind of considered as a continuous source. We're never going to exhaust that source during our carburization event because the atmosphere is just so full of them. Or for things like semiconductors, what we would typically do, we can sputter a very thick layer of material on the surface, okay, which, if that layer thickness is much, much greater than the width of our grain boundary, then this can also be considered as a continuous source. Okay, so often when we dope semiconductors, this is how we would do it. We would put a very thin layer and then heat it up. Right? With semiconductors, grain boundaries are bad, right? Because what happens is we get accelerated diffusion of whatever our surface layer is we're trying to dope our material with into our grain boundaries faster and creates a localized concentration. When we have a localized concentration of elements that we use for doping, the properties will be different from place to place in our semiconductor. Okay, so during our annealing stage, the atoms diffuse from the surface, okay, from up here, into the specimen in two ways. Okay, so atoms can directly diffuse into the grains themselves, right? But we know straight away that the diffusion coefficient of the grains themselves is much, much less than the grain boundaries. Okay, and this is what we would do for a typical doping type setup in a single crystal silicon in a semiconductor world. All right. Or they can take this much faster route along the grain boundaries. Right, so in turn, the atom which diffuses along the grain boundary eventually leave it and continue to diffuse into the lattice regions. Right. So from the surface, our atoms will come down our grain boundaries. They will diffuse much, much faster along our grain boundary. Critically, they will go to a deeper depth than any surface diffusion. But in the same time, we have to remember that that grain boundary is also in equilibrium with our lattice as well. Okay? So our atoms will diffuse down the grain boundary, but they will progressively diffuse also into the lattice. Okay? So this can give composition gradients around our grain boundary, okay, depending on the flux of atoms diffusing into those grain boundaries. Okay, so this gives rise to a volume diffusion field around these grain boundaries. And we have to account for that tapping off of atoms into our grain in our underlying equations for describing this event. Okay, so again, we try to make some very, very large approximations here in what's actually going on. Okay, so mathematically, we try to make it as simple as possible. We're going to say the diffusion process is described by two coupled equations, okay, that are very, very similar to fixed second law. So the stuff that you learn about with Rakesh are things diffusing into a homogeneous bulk material. Right. So all we're really looking at and measuring is essentially concentration profiles relative to time based on a diffusion coefficient. Okay, so we have two coupled equations here. Okay, One is looking at the diffusion of the material from the surface into the bulk. Okay, so concentration profiles relative to our X and Z ordinate system. And again, if any of you are balking at equations and things, I'm not expecting you to memorize equations for an exam. Just know what these equations are actually talking about and what their effects are. All right. The other coupled equation that we're using here is our concentration gradient along our grain boundary, okay, in terms of X, Y, and Z. But we also have to take into account this tapping effect of atoms leaving the grain boundary and moving into the bulk. And that's what this part of the equation here is all about. Okay, so this is usually going to be a negative concentration profile, okay, which is detracting away from the concentration of these atoms in our grain boundary. Okay, so atoms into the grain boundary, atoms going out of the grain boundary, okay, below the surface. So we kind of get that, how the mechanism's working here, bringing atoms in from the surface. Just for now, we're assuming an infinite supply of atoms from the surface. Some of them are going into our surface at a very, very low rate, okay, because of a very, very low diffusion coefficient compared to the grain boundary. Other atoms are going straight down the grain boundary and then being gradually tapped off into the bulk or into the lattice. Just in case any of you are wondering, and we do cover this a little bit later on in today's course, the diffusion across a surface is typically faster again than the diffusion in the grain boundary, which is then orders of magnitude faster than diffusion into the bulk or into the lattice itself. Okay, so in terms of supplying our grain boundaries with atoms and things, okay, typically this surface diffusion coefficients are much, much faster, so we can move atoms across the surface or from our environment into the grain boundaries fast enough so that they don't really run out, okay, unless we've got a very, very thin layer which is going to get depleted over time. Right, so any solution of equations 30 and 31 need to meet the surface condition, which can be different in different experiments. Again, we'll talk about it a bit more later, as well as the initial and boundary conditions. Okay, what are the concentrations at x equal to affinity, y equal to affinity, so on and so forth. Okay, the joining condition between the two functions. Okay, the concentration within the material and the concentration at the grain boundaries in terms of depth. Right. Depend on whether we're examining self-diffusion or impurity diffusion. Right. So sometimes we want to know how fast an atom of the same material can diffuse through the material. Right. And this helps us with things like grain growth and recrystallization and things like that. If we know how fast an atom can move within its own material, within its own lattice, this helps us with those calculations. Right. But when we're talking about impurities and things like that, these can be very, very different in how fast they can move and will affect what is actually going to be formed from those atoms or elements, whether we can form an intermetallic or whether they just sit there as an interstitial lattice impurity, things like that. Okay, so for self-diffusion, the joining condition simply reflects the continuity of the concentration across the grain boundary. Okay, so what we're trying to basically say is for self-diffusion, the concentration across the grain boundary is going to be the same. It's the same material. Okay, so it's a flat line. It's a constant. For impurity diffusion, the joining conditions involves the equilibrium segregation factor, S. Okay, so it's basically the same equation here, but we've also got this little fudge factor here, which basically accounts for differences in diffusion, coupling ability, chemistry, things like that, of an impurity element. Okay, which starts to alter our equilibrium. So it's fairly straightforward and simple. How we're looking at these things. Okay, so talking about the surface condition again. We've already talked about a constant supply, right? So in Fisher's original model, he postulated that a constant source condition at the surface would apply. Okay, so concentration x at point 0, basically over time is going to be a constant, C naught. Okay? This condition is also called the thick layer condition because it can be established by depositing a thick layer of diffusant. Okay, so H here being the thickness of that layer, being much greater than basically the factors that drive our diffusion rates and diffusion depths. Okay, diffusion coefficient multiplied by time, square root all. Right. So when we have a very thick layer, we can assume that the supply is constant. The constant source condition also applies when diffusion takes place from a gaseous phase, and again we've already used the example of carburization. So that's nice and convenient. If we've got a very thick layer, or essentially an infinite environment supplying us with our diffusant, okay, then we can consider it to be a constant. So in our other condition, okay, we have what's called an instantaneous source or a thin layer surface condition. Okay, it postulates that the surface diffusion is much faster than the volume and even grain boundary diffusion, which results in a uniform surface concentration near the grain boundary surface intersect. Okay, so again, assuming this constant concentration or uniform concentration. Okay, and then the respective surface condition is then defined by this type of equation here. Okay, where we have this M factor, which is the amount of diffusant deposited per unit area of the surface. Right. Once that's depleted, okay, essentially our reaction will stop. Okay, so we have a limited depth, right, dependent on how much material we actually have at the surface. Okay, so we consider it to be a constant supply until it runs out. This condition assumes that our thickness is much thinner than our diffusion depth profiles over time. Okay, so once we run out and we end up with, okay, we might have a specific depth at which we can penetrate into our material, okay, and then we essentially stop. Once we do stop, okay, our equation dynamics change. Because although we can't diffuse any more material in from our surface into our grain boundaries, the material can still continue to diffuse from our grain boundaries into our material. Okay? So then we would essentially reach, over a long period of time, based on the diffusion coefficient of the matrix, a uniform distribution of that diffusant. Right. Whereas under constant supply conditions, we're always going to have this continuous gradient until it's completely saturated, which could be an infinite period of time. All right, so our basic equations, this Fisher model, okay, 1331 can be solved analytically. Okay, so the integral representations of the exact solutions for the constant and fast surface diffusion condition have been solved, but again, the practical significance of the exact solutions is really limited. Okay, they're very complicated in their form, right? And in practical terms, any mathematical solution is only useful if it offers a way to process the experimental conditions. Okay, so again, it's about as useful as our classic nucleation theory. It kind of helps us with understanding our mechanism, but typically these things would be measured. Right? How do we measure? How would we measure them? How would we measure diffusion rates through grain boundaries? We would do, so if we took our lump of iron, we're trying to case harden it, we've thrown it in our carburization furnace for so many hours at a certain temperature, okay, and we wanted to know what our depth of carburization was. How do we determine that? Well, we physically have to cut it up and measure the amount of carbon over our depth profile. Yeah? So yeah, it's a very physical measurement. Right? And we're trying to tie that back to a fundamental equation. Right? Once we have several or numerous data points, we can start to see, all right, if I'm diffusing for this amount of time at this temperature, I get this depth profile here. The width of my grain boundaries I can also measure. Okay, we can plug it back into this equation. Right? If if I do this 3 or 4 times for different types of conditions, I start to develop an array of data where I can say, all right, if I want a carburization depth of 50 microns, okay, I know I can either anneal it in our carburization furnace for 2 hours at 1100 degrees, or I can do it for 4 hours at 800 degrees, or something like this. Okay, so we can start to develop diffusion rate profiles based on data. But again, always it's based on measurement. We're using these equations just to describe a curve or a point, okay, for these sorts of processes. We need our initial data input to define what is D, what is dB. Okay? We need to measure delta. We can alter this concentration. So, grain boundary diffusion measurements, okay, would typically employ a radio tracer. Okay, if we're looking at self-diffusion, we might get a radio tracer element that we on purpose introduce into our surface layer so that we can then see how far that same element is diffusing into the material and along the grain boundary. Okay, so we can't pick up chemically an element that's the same within itself because they're all the same. Yeah? So what we do, we pick up our radio tracers, okay, so an isotope of the same element, and then we detect the level of radioactivity at a certain depth profile. That way we can determine the diffusion coefficient of self-diffusion within a material along a grain boundary or within the lattice. Okay, and then what we would do, we'd do serial sectioning of the thing. Okay, so we can do it by polishing steps, where we take away a couple of microns at a time, do a radioactivity measurement. Okay, what is the radioactivity of the material in terms of counts at a certain depth? Okay, until number of counts tails off to 0 or statistically insignificant. Right, or we can use it using the focused ion beam down in the microscopy unit, cutting thin slices of the material and then analysing it. So typically we'd use a gamma detector or a liquid scintillator for detecting radiation at those sorts of depths. If we're trying to measure something that is different, so a different element, we have other analytical techniques for doing that. Okay, as soon as we have a chemical difference, we can use chemical analytic techniques, so things such as EDS, EPMA, down in the microscopy unit. Right, so hopefully you're sat 2003. We learned a little bit about those techniques. Okay. So we can then, essentially doing sectioning of our grain boundaries and our surface, we can then do accurate elemental characterization around the grain boundaries and the surface. There we can develop our composition profiles and then, again, plug those back into our formulas to see, under those conditions, how far things have diffused into our material. Okay. All right. So another of the two things that we actually look at, okay, so we try to define our D and dB of our materials, okay, but a critical part of our analysis of grain boundary diffusion is this distance here, delta, okay, so this actually defines the ability or the flux capability of the material, okay, which is plugged into our equations, right, so we can make some assumptions about delta. Typically, okay, delta in most materials is about 0.5 nanometers wide. The grain boundary, where two grains meet up, on average, in most materials, 0.5 nanometer. Okay, it varies in some materials. Okay, it can depend on lattice parameters. Okay, and it can depend on crystal structure of the surrounding grains, and also the orientation of those grains next to each other. Different orientations of crystal structures will give fatter or narrower or isotropic types of grain boundaries, which alter diffusion kinetics. Okay, but again, we can actually measure grain boundary width, particularly if we already have a segregant sitting in them. And here's an example of bismuth sitting on a grain boundary in nickel. Okay, so in our TEM, we can go in here and say, all right, I can see the bismuth is sitting there. Okay, at our grain boundary, that's a good indicator. We can continuously zoom in the TEM until we get down to atomic resolution. Physically measure the width of our grain boundary. And we can also measure that width at different orientations as well. Okay? So we can accurately measure our delta here for our given material for a different crystallographic orientation, or just try to find an average for our material. Okay. Having that critical value there can determine the flux or the rate at which atoms can diffuse down through our material. Right, so this falls into our X parts of our equations, and trying to plot diffusion profiles within the grain boundaries and around them. Alright, so hopefully you've kind of got a little bit of a grasp on grain boundary diffusion. Key takeaways are, usually we've got a constant supply of impurity or something at our surface. Okay? Grain boundary diffusion is much, much faster than diffusion within the bulk or within the lattice. Okay? Grain boundaries are superhighways for diffusion. Okay? The surface is faster again. There's very few restrictions on diffusion across the surface. Okay? We're only in contact with a few atoms on our surface for another atom to migrate across it. Okay? Hopefully you can appreciate if it was surrounded by atoms, much more difficult to move. The type of profile that we're going to get of diffusion in the surface of our material does depend on a few other things. Okay? The obvious things like temperature and time, okay? Because we are relying on diffusion into the bulk from both the grain boundaries and the surface most of the time. Okay? So temperature and time will play a factor to that. Right? But other things that do come into play are the distances between our grain boundaries. Okay? If we have a very, very fine grain material, okay, the spacing between grains is going to be very, very small. Okay? So then our diffusion distance is then going to affect the profile of diffusion depth in our material. Okay? If our grain boundaries were spaced much, much further apart, okay, because that diffusion rate into the bulk is much, much slower, that's going to give us a different type of profile in our diffusion depth. Right? So, grain boundary diffusion, complex, involving several elementary processes, such as direct volume diffusion from the surface, okay, so coming down from the surface, diffusing along the grain boundaries, partial leakage of the diffusant from the grain boundaries into the bulk in this direction, okay, this direction, and subsequent volume diffusion around the grain boundaries. Okay, so once we have material here, it'll continue to diffuse into the bulk of the grain boundaries themselves. So depending on the relative importance of these processes, different diffusion regimes or kinetics can occur. In each particular regime, one or two processes control the overall rate of diffusion. Each regime dominates in a certain domain of annealing temperatures, times, and grain sizes. Okay. So we typically talk in Harrison's classification, okay, when it comes to the different types of grain boundary diffusion and profiles that we see. Okay. So Harrison proposed the first and still the most widely used classification of diffusion kinetics in a polycrystal with parallel grain boundaries. So again, oversimplification. Okay, grain boundaries typically aren't parallel. Right. Can we think of a case where grain boundaries might be parallel? When do we get parallel grain boundaries in a material? We've seen a few examples already in class. Where might our structure have some kind of anisotropy? An excess of grain boundaries running in certain directions. There's two cases, both of them are really common. So we're just thinking about things in terms of making it easy to describe mathematically, but in reality, here's our material. Here. What would the grain structure look like if we've just passed it through a rolling mill? Directionality and isotropy. Essentially, our grains are all going to be flattened side, surface, into the material in this direction, or if we just were in a certain atmosphere, okay, what would our diffusion profile look like in this material if all of our grain boundaries are parallel, lined up in that direction? So grain boundary diffusion is more rapid in the direction of the grain boundaries. Okay? If we're surrounded by, say, carburizing atmosphere or something like that, okay, if this end of our material is actually exposed, and for an instance in time, okay, we'll probably end up with a diffusion profile that might look something like this. Okay, so atoms trying to diffuse from this surface, they might go rapidly in this direction, but once they hit and intersect, they're going to be diffused more rapidly in this direction. Yeah? Whereas if we've got more grain boundaries aligned in this direction, we've got our diffusion superhighways operating in this direction much more rapidly. Okay? That's for rolling. What's another case that can cause isotropy in a material? Anyone ever seen a casting before? Section of a casting? We have already in class. Remember our inoculated sample? Blue's not coming up very well. So in a cast sample, grains will typically grow in the direction of cooling. Yeah? We get dendritic structures. Severe undercooling, growth, direction of cooling affects things. So we actually have dendrite fingers pointing into the material radially, like that, in a raw casting. Okay? So again, then sometimes the extent to which they can grow depletes, and we can get equiex grains in the centre. Sometimes they'll grow all the way to the centre. Essentially, we have something that's anisotropic in terms of what it can do diffusion-wise. So, grain boundaries being our superhighways, we can diffuse something very, very rapidly to this depth here, but once we hit our uniax grains, diffusion then becomes more omnidirectional. Okay, and we'll slow down. It's that directionality in our depth profile. Okay. Do you understand that? You grasp that? Alright. Okay. We have to always think in terms of temperature and time. Okay, so for a given material, our D values, so D, diffusion coefficient of our lattice, and dB, diffusion coefficient of our boundaries, are essentially going to be the same. Or we're going to be assuming they're relatively close to being the same. Okay, so then it becomes a matter of how those D values affect our material and how these other types of parameters, grain boundary spacing, temperature and time, affect our depth profile. Okay, so the A regime, this case here, is observed at high temperatures after very long annealing times. Okay, and when the grain size is small. All right, so if we want a nice uniform depth profile of diffusion, grain boundaries, or even without grain boundaries, all right, we want high annealing temperatures, okay, because D is affected by T, temperature, okay, and time, our concentration is then affected by time. All right, so higher temperature, we can diffuse more quickly, okay, over longer time, we've diffused greater distances. If our grain boundaries are nice and close together, then the reliance on the diffusion coefficient of our lattice becomes a little bit less. Okay, so typically, all right, the volume diffusion length, okay, which is given by dt, square root, is larger than the spacing of d. Okay, distance between our grain boundaries. So the volume diffusion fields of neighbouring grain boundaries overlap very extensively, okay, giving us a nice uniform profile. All right, so for type A, this is our condition. Diffusion coefficient by time, square root, is much, much greater than our grain boundary spacings. So hopefully you can appreciate that if we have a lower temperature, or our diffusion annealing time is shorter, or the grain size is larger than in the previous case, diffusion takes place in this regime here. Okay? So basically dB is overriding D significantly, okay, and the distances at which these atoms can diffuse. So we don't quite get a uniform profile. Right? We have a higher concentration of the elements along our grain boundaries and in closer proximity to our grain boundaries, okay, as we go deeper in our profile. So in this case, satisfy regime B, right? Delta, our spacings, okay, our diffusion coefficients are much, much less than D, okay, and delta is much, much less than these two. And type C is basically the greatest extreme, where we have a very, very short diffusion time, okay, or maybe very, very low diffusion temperature, or it could be done at ambient temperature, okay, over very, very long periods of time. Okay, so typically if we set something at atmosphere at a long period of time, if we did have some kind of environmental contaminant in here, it will only really move down and along through our grain boundaries. We mightn't even hit an activation energy high enough for diffusion to go into our lattice. Right. So we would only have diffusion into our grain boundaries over time. Right. We'll just check what we've got here for a movie, and then we might take a quick break. Hopefully the movie's going to start today. Okay, so this is just a simulation of diffusion along grain boundaries. Okay, so again, we can use our fundamental equations. Start again. From a surface condition with 100% diffusant, okay, which is noted by yellow, right, and how the material over time diffuses along those grain boundaries and then progressively into the core of our grains. So obviously at the surface where we have a concentration profile, at the surface is very high, our diffusion coefficient through our matrix is sufficient enough to start to really supply this particular grain with a high concentration of our diffusion. Okay, but we can see clearly the concentration of diffusion along the grain boundaries is going to be much, much higher. Right? And these grains down here will not see the effect of diffusion for a significant period of time, okay, until our concentration profiles live. Right, we might take a break there before we get on to other bits and pieces. So we'll take 10 minutes. Any questions, come on up or raise your hand. But then we'll get back into it. low temperature, or it might be a very, very short period of time. Okay.
So it's low temperature plus the short time.
It could be either. So this here can be very, very early stage of this here.
Yeah.
Okay, so the diffusion in a very, very short period of time, very, very rapid down the grain boundaries. Okay. So in a short period of time, diffusion only down the grain boundaries may occur.
Yeah.
Right? But this is typically in the case where we have very low temperature. Right? Very low temperature. And it could be a very, very long time as well, depending on the energy required for diffusion in the bulk.
So you mean at low temperature the photon can't diffuse out of the grain boundary?
Very, very poor. Not enough energy to do it. Okay? So they preferentially will just stay in the boundaries or move around in the boundaries very, very slowly.
But why at the low temperature the photon can still diffuse into the grain boundary?
Just because the grain boundary has a different energy condition. Okay? So, and we'll get onto it in a little bit. The structure of the grain boundary, there's lots of gaps and voids and holes.
Okay.
So it's high energy. So atoms will be attracted from the surface to a high energy site. And if this is all a high energy site, they will continue to move through because they can help lower the structural energy as well.
Yeah. Yeah, understood. Thank you.
Okay guys, we'll get started again. Okay, so we just had one question there about type C type of diffusion. Again, this system is going to be, for example, at room temperature, okay, the energy of the system is going to be very, very low. Okay, so diffusion in the lattice is going to be very, very unlikely, or again, very, very low. Okay, because the temperature is so low. Atoms from the surface of the material are going to be attracted to high energy sites. Okay, now a grain boundary is a high energy site. Okay, it's disordered, has gaps and voids in it. Okay, so any rogue atom is going to be attracted to that site to try and minimize the structural energy of the system. Okay, and once it's in proximity to the grain boundary, it's then free to migrate at a high diffusion rate through that grain boundary. Okay, so typically very, very low temperatures is where we will get type C. All right. So in exactly the same way as lattice diffusion follows an Arrhenius temperature dependence, so does grain boundary diffusion. All right. So we still have an activation energy and a temperature dependence. Okay, for grain boundary diffusion, it's just Q for the grain boundary is going to be much, much lower than Q for the lattice. Okay, so QB of the grain boundary is about a factor or two smaller than the activation energy Q for the lattice diffusion. Okay, so more exactly, in most metals, QB over Q is equal to, or usually between 0.4 and 0.6. Right, so activation energy is around about half that of the bulk or the lattice. Okay. When we plug that back into our equation, basically what we see is grain boundary diffusion can be 4 to 8 orders of magnitude faster than volume diffusion, depending on the temperature. Okay, so we're not talking 4 or 8 times, we're talking 4 or 8 orders of magnitude. So this is, hence, grain boundaries being superhighways for diffusion compared to the lattice in the bulk. All right. Here's a couple of data sets here where we see grain boundary diffusion rates and activation energies. All right. It also differs depending on the crystal structure of the material. Okay. So remember, we've got a couple of different types of crystal lattices that exist. Okay. How those types of crystal lattice meet up at a grain boundary are going to be different. Okay. The sizes of the gaps and the energy associated with those highly disordered grain boundaries is going to be a little bit different depending on the grains that are making them up. Yeah. So we can see here that BCC has a slightly higher or slightly more significant activation energy for grain boundary diffusion compared to FCC, which is the lowest in HCP. Right. But all in all, they're not too far away from each other. This does affect our diffusion rates a little bit, just by these factors. Okay, so essentially by this we can get a difference of 2 orders of magnitude approximately between those different crystal structures in terms of our grain boundary diffusion. All right. So in the grain boundary itself, okay, we've actually got experimental evidence suggesting that grain boundary diffusion takes place by the vacancy mechanism. Okay, so what happens is as an atom approaches a grain boundary and becomes incorporated in the grain boundary, the way that it diffuses is by the creation of vacancies, so holes in that structure, volumes, free volume in that structure, shifting and making way for it to diffuse through the structure. Okay. Although we can't write off alternative mechanisms, okay, especially interstitial mechanisms where atoms can actually fit through the gaps between other atoms depending on their size. Okay, and of course our example here of carbon or nitrogen moving through steels is not uncommon. The size of an iron atom compared to the size of a carbon atom is quite different. Okay, so even if we've got an iron atom space in something close to a BCC or a distorted BCC structure at a grain boundary, okay, the gaps between those atoms are essentially a lot larger when the difference in the size of the atoms is large. Right? So we can fit those small nitrogen or carbon atoms through the gaps interstitially between the much larger metallic atoms. Right? Computer-based simulations, okay, so this is first principle simulations where we can effectively simulate what's going on in the interaction between atoms based on outer atoms in their first and second electron shell. All right. Suggests that the full description of grain boundary diffusion should include both vacancy and interstitial related mechanisms. All right. But also we can get long jumps involving simultaneous displacements of 2 or more atoms in grain boundaries. Okay, so this is big. All right. So usually diffusion via vacancy or interstitial movements. Okay, those movements are typically the size of 1 atom spacing or less every time that atom makes a diffusional move through our system. If we can have a jumping mechanism where atoms can essentially hop 1 or 2 atoms, even 3 atoms in one spread, that would typically in a crystal lattice be very difficult, if not impossible. Okay? But because we do have large gaps and things in our grain boundaries, this becomes possible. So already we're operating at a rate 3 or 4 times faster in terms of jumping mechanisms of diffusion through grain boundaries. Right. There is a little bit of a movie here that shows you vacancy movements in a crystal lattice and jumping movements in a crystal lattice. It's only kind of semi-relevant, but it gives you a little bit of an idea. I'm not going to play it here today. You can play that one in your own time. All right. But basically, this movement, okay, atoms displacing vacancies in a structure, moving interstitially between the gaps in atoms, okay, or essentially jumping 1 or 2 atoms at a time where possible. All right, now, types of grain boundaries. All right, so grain orientation and grain boundary diffusion and isotropy. Not all grain boundaries are equal. All right, the width, okay, so our delta of our grain boundary is going to depend on a number of things. Okay, the size of the atoms it's made out of, for one, right, and the nature of the grains that make up that grain boundary or sit on either side of that grain boundary. Their crystal structure and their orientation relative to one another. Okay, so if their crystal lattice are very close in alignment, okay, so my fingers here, crystal lattice, they're close in alignment, okay, the grain boundary is probably going to be fairly narrow. Okay, because the amount of atoms that have to be displaced to actually make up that grain boundary are fewer. But if their alignment is a long way off, okay, we're going to have a wider grain boundary. When we have a wider grain boundary, what have we got? A wider superhighway. A wider superhighway means we can get more atoms down. Okay. So as atoms attempt to bond to each other across the grain boundary, the crystallographic orientation, or the grains on either side of the boundary, will have a dramatic effect on the configuration of the atoms within the boundary region. Okay. So this is a structural factor, okay, which determines how the atoms are configured in space in the region, which naturally is going to have an effect on diffusion in that region. So this diagram here might be a little bit difficult to understand, right? But basically, what it is the diffusion rate, essentially, on this axis, and the difference in orientation between the two grains that make up the grain boundary. All right, so for this particular system, all right, this is for silver. Silver's an FCC material. Silver has one of the fastest diffusion coefficients of all materials. All right, and here we've got our orientation dependence of self-diffusion. So this is silver atoms moving within silver based on orientation. Okay, and what we find is, okay, out here when we have 0 degree difference in orientation between the grains, basically diffusion coefficients are going to be, hang on, this is misorientation, sorry. Symmetrical tilt grain boundaries, okay. Oh, on the 001 plane, okay. So this is the difference between our boundaries in the 001 plane, right? So what we can see out here at lower differences in our boundaries, okay, diffusion coefficient rates tend to be low. At approximately, we will say, 45 degrees to one another, okay, we see the diffusion coefficients increase dramatically, right? And then once we move away from 45 degrees again, they drop down further. So basically what this is indicating, as the misorientation between those two grains increases and decreases, we have an optimal angle at which diffusion is very, very high, and then we move away to less optimal angles where diffusion is very, very low. Okay, so again, the orientation of those grains is affecting the grain boundary width, which affects the flux of atoms going through those grain boundaries. Okay, and the structure of those atoms within the boundary. Okay. So here's a couple of examples here, right, of how we can perceive viewing what's going on in these grain boundary structures. Okay, the curvature of a grain boundary can affect diffusion. Okay, the size of the lattice itself can affect the shape and the width of the grain boundary, and then the misorientation. So here we're at a misorientation of about 45 degrees. Okay, you can see some sections we have very, very wide grain boundaries, some we have much, much closer grain boundaries. Okay, so as these atoms attempt to bond to each other across the grain boundary, crystallographic orientation on either side of the boundary will have significant effects on the configuration of atoms in there. Okay, and it's different for each system depending on the crystallographic relationship in a given crystal lattice. Okay. And we've also touched a little bit here now on how the curvature or the shape of our grain boundary can affect diffusion. Obviously a straight path, okay, and again just think of the highway concept. All right, a perfectly straight road, we can go much, much faster without any impedance. Yeah? Whereas if we start to put tight curves, narrow curves, multiple intersections, we can slow down diffusion. Right? But we've also got to remember that at intersections, we've got a larger volume for diffusion as well. Right? Okay, so here's just another example, right, of grain boundary diffusion. This one's in gold. Okay. Sorry, it's gold diffusion in copper. Okay, so we've got an impurity atom. Gold is larger than copper. Okay, so this also makes a difference. Is the atom larger or smaller than our lattice, our host lattice? Okay, so if gold is smaller than copper, what are we eliminating in terms of our mechanisms? Gold's larger than copper, sorry. So basically, if we have an atom that's larger than our host atom, interstitial diffusion becomes negligible. Okay, we can't fit a big atom through a hole or spaces in small atoms interstitially. It has to be by vacancy movement. Right? So diffusion of gold in copper is likely going to be slower than copper in gold or carbon in steel, because gold is larger. We eliminate our interstitial diffusion. Right? But again, we see some very, very significant changes in diffusivity based on the orientation between our crystal orientations. Okay, so here it's not just a clear-cut case of here's our maximum, here's our minimum. Okay, sometimes diffusion might become near impossible at specific orientations. Okay, and then once we exceed that orientation, it goes to something very, very high. Okay, so once we go over a high angle tilt boundary or something like that, diffusion is allowed and happens again very, very quickly. And this is going to occur at some very, very specific crystallographic angles. All right. So key takeaways here are that the crystallographic orientation is going to affect diffusion rates, okay, based on how crystallographic orientation changes the width of the grain boundary, the shape of the grain boundary. Okay. Okay. Now, in the same way that crystallographic orientation, okay, can affect the structure of the grain boundary, so too can dislocations residing at grain boundaries. Okay? So local strains and defects can assist in atom mobility, vacancy mobility, and interstitial sites and sizes. Right? So this kind of ties back a little bit to our recrystallization lecture last week. Okay? If we impart deformation to our material, we're putting more defects into it. And dislocations move, they will typically move to a grain boundary, where they're either going to be tripped up by the grain boundary or other dislocations already sitting at the grain boundary. So if we've got a high number of defects already sitting at the grain boundary, this is effectively like making the grain boundary wider. Yeah? More defects moving into our lattice when we have dislocations and vacancies caused by deformation. Okay, so if we have a deformed material, okay, this too affects grain boundary diffusion. We're making that grain boundary effectively a little bit wider. And we've got localized spots of high energy and low energy created by that deformation process. Okay. So this one here is a very nice figure showing diffusion coefficients or log of diffusion coefficients on this axis versus temperature. Right. So naturally, diffusion in an FCC lattice, as our example, is much, much lower, okay, than diffusion in a lattice that contains a significant amount of dislocations, dissociated dislocations, for example. So we're putting more defects into our material. Right, we've put some cold work into our material, created more dislocations. Those dislocations tend to pile up at the grain boundaries, making our grain boundaries wider. So naturally, diffusion coefficient in our bulk material has increased. Here's just a comparison to BCC at grain boundaries. Right. So here's our comparison here with our diffusion coefficients along grain boundaries when we have undissociated dislocations piled up at them. Okay, so this is higher again. Right. And here is our diffusion coefficient on an FCC material at the surface, so surface migration, which we've already said is faster than everything. Okay. So key takeaway, and this one kind of pops up in the exam quite a bit. All right. Diffusion across the surface is faster than at the grain boundaries. Okay. When we have deformation, it's going to be faster again. Okay. And all of these things are much, much faster than diffusion within the bulk or within the lattice of the material. Going to make a few quick notes on surface diffusion. We're nearly done for today. So surface diffusion is a general process involving the motion of atoms or molecules. Okay, so remember our grain growth lecture where atoms were moving through our diffusion boundary layer, adding to the surface, atoms, okay, or clusters at a solid material surface. The process can generally be thought of in terms of particles jumping between adjacent adsorption sites on a surface, similar to vacancy hopping in grain boundary or in the bulk, but obviously with many more vacancies. Okay, so you can think about the surface, okay, an atom or adatom molecule jumping across the surface as having almost infinite vacancies to hop into. Right? And this is why diffusion across the surface is so much faster. Right? If we've got an infinite or nearly infinite number of vacancies to hop into, okay, diffusion is going to be faster. In the grain boundary, yep, we've got vacancies and interstitial sites, easier to hop through. Okay? In the lattice, we've got very, very few of these vacancies. Okay, so much, much more difficult for an atom to hop through. So while surface diffusion can be described by phenomenological equations like Fick's law, okay, so again, applying a very, very basic fundamental equation to something that is a fairly complex and multi-step process, fundamental calculations are very complex. Right? The Langevin equation is probably the most simplest case, but I haven't even bothered putting it up here because it's this long. Okay? And these components here, here, and here change depending on the system and other boundary conditions. All right? Way beyond what we're covering in this course, and probably tricky for doing a PhD or something like that. All right? So from a purely observational perspective, the diffusion via the surface is relatively fast compared to a grain boundary or lattice and bulk diffusion. Okay? So key takeaways are just here on this slide. So the diffusion coefficient, diffusion rates across the surface are going to be much, much greater than that of the grain boundary, which are going to be much, much greater than that of the lattice or the bulk. This is generally a result of the activation energy, Q. We've already learned about Q with Rakesh and a little bit here. For the lattice being much higher than that of the grain boundary, which is again higher than that of the surface. Okay, so we've got the inverse relationship, okay, for activation energy. All right. And typically, the ratio of these, so activation energies, and we've had a little bit of a look at activation energy for grain boundaries versus the lattice already. Okay, but typically, the activation energy in the lattice, right, is 4 times that of the grain boundary relative to the surface. Okay, so these are the types of ratios that we're looking at here of our activation energies for those 3 different regimes or types of diffusion. Okay. It can also be looked at in the number of bonds within our structure that need to be destroyed and recreated for a diffusion event. All right, so again, across the surface, we've spoken about it in terms of vacancies. In terms of bonds, how many bonds is an atom moving across the surface in contact with? Maybe 3 or 4 underneath it as it moves. In a grain boundary, how many bonds is an atom going to be in contact with as it moves through the grain boundary? Okay, depending on its coordination, could be up to 10, 7 to 10. In a lattice, coordination numbers of an FCC system, 14. Okay, so again, the number of bonds that are actually associated with that atom and trying to break and recreate those bonds as it tries to move through a system. Okay, what have we got here? Oh, okay. So this is vacancy hopping across the surface. So that's live out of a TEM. What's our other one here? Surface diffusion. Okay, so we'll hit pause. So this experiment here, incredibly basic. Okay, diffusion within a liquid surface compared to within the bulk. Okay, so what's happened here? We're dropping a liquid into another liquid. So this is simply a dye or something like this. And you might have seen this yourself when you've been messing around in the kitchen or whatever else. Okay, so here's our droplet of dye. Here's our bucket of water. What happens? So just watch it carefully. See how it diffuses and disperses within the media. Okay, do you see that? Diffusion across the surface compared to diffusion into the bulk. Yeah? So we can see it moving across the surface incredibly rapidly. Once it reaches a critical energy, breaks the surface tension. Okay? Yet we're not seeing hardly any diffusion going down into that liquid, yeah? There could be some density dispersion effects going on there, but essentially that's what it's trying to demonstrate. diffusion across the surface much more rapid than into the bulk. Okay. So again, back to these types of plots here where we're just trying to show you that diffusion across the surface versus the grain boundary versus the bulk or the lattice, okay, in a number of different systems. Right? So it's essentially been proven, shown quite fundamentally and without any doubt that surface diffusion is much higher, and we're talking orders of magnitude here. So here's our diffusion coefficient, right, for a given temperature, and we can see here, what's this, 1, 2, 2 orders of magnitude there, 3 orders of magnitude there, and another 4 orders of magnitude down here to volume diffusion. We can also start to see here the effects of activation energy on diffusion. We have to get to very high temperatures for volume diffusion, all right, to actually become significant in terms of our diffusion coefficient. All right. So this is again that example that I showed you, the type C, types of grain boundary diffusion, where we only had diffusion going down the grain boundaries. So we might have been in a temperature regime over here, or we haven't even started to activate volume diffusion over here. All right. So again, this relates to our different regimes in grain boundary diffusion as well. All right, we won't show that one because that's the tutorial. Okay, are there any questions on surface grain boundary diffusion, or even bulk lattice diffusion? So again, and we'll cover this in our tutorial for exam. All right, key takeaways are these differences in diffusion coefficients of those 3 types of conditions: surface, grain boundary, and lattice. The inverse of that is the activation energy. You can get it from Fick's law. Right? Look at the equation. If this one goes up, that one must go down. All right? This is the actual thing. Like, it's usually in question 3 or question 4 of the exam, and students often mix it up, get it around the wrong way. I supply Fick's law as an equation on the exam, and they don't bother looking at that and trying to figure out the maths. Okay, they've just tried to memorise it. All right? So if in doubt, just go back to Fick's law on this one. Fick's second law. Okay. So on Thursday, we're going to be having a lecture on segregation and homogenization. All right. After that, we're into tutorial time. Okay, and studying for the exam. So I'll run tutorials probably next Monday and Thursday for the exam. Presentation,
yeah.
Final presentation.
Yeah.
So I don't timetable this, Chris Sorrell does, because it's still technically part of his T1 course, right? So what normally would happen, he will release a timetable to students, probably he will let you know in week 10, and it's usually in week 11, week 12. Okay? He usually tries to do it before the exams start.
Before the exam.
Yeah, so probably week 11, but Chris determines this one, not me.
Understood. Yeah,
Yep.
thank you.
Okay.